initiative to accelerate the adoption of advanced manufacturing with a focus on additive manufacturing in Singapore and in Asia Pacific. Today, I'll bring you through a journey of where Siemens has been in the last 6 to 10 years. And I must say, over the last year that I've been back in Singapore, NAMIC has been instrumental in bringing together the whole ecosystem for additive manufacturing into Singapore. And with our partnership announcement this morning, we want to leverage on that with our partners within the current ecosystem to kind of demystify what advanced manufacturing is and what additive manufacturing really is. So let us start on the Siemens journey. AM has progressed quite a fair bit in the last couple of years. We've gone from doing a like-for-like micro-welding process where we print as is for spare parts, where the performance is already good enough. We've created lattice structures to lightweight parts and components to improve the performance and lightweight and the durability of these parts. We have lowered costs such that now polymers will potentially take over metal parts. And today, we are looking at new materials. That's at the forefront of additive manufacturing. We have gone beyond just prototyping. We've gone beyond just exploring what is additive, at least within the Siemens world. Some of the hurdles my colleague Sylvia has mentioned, certification, validation of the process, of the material. There's limited supply of raw materials, especially the exotic ones that we're creating today. There isn't a qualified or certified material supplier, if you will, because they're so customized that there isn't one authority that can really justify and certify all these new materials. The development and validation is still very much a manual process. We're collecting tons and tons of data, putting it into AI and machine learning to try and suss out what are the combinations of these materials that could really work in the real world. So in Siemens, we've been collecting this data for the last 6 to 10 years. I come from the division Energy, and we produce gas turbines for the power generation and energy sector. And our gas turbines have been in mass serial production using additive manufacturing. And we have already produced parts that are already commercially viable at our customer sites over the last 6 years. And this is our journey. We have helped all these verticals and industries convert from lab to fab, from R&D to actual production, to actually embark on this journey to have additive manufactured parts. We feature very strongly in oil and gas and mobility, which we use ourselves, so we are end users of additive. And how do we bring this entire picture together? How do we bring the adoption rate to the next level, as I mentioned earlier on? These are some of the efforts or the path and journey that we've been through over the last 6 years. We started off with repair, with the burner tip, where we only sinter and laser on the top bit, as you see here, from a repair standpoint. We moved on to commercialize parts fully 3D printed in rapid manufacturing. So we have what we call a digital inventory. On demand, we want this part, we print it on the spot with a bucket of powder. We have also developed our design expertise in developing this, what we call the Ibuma burner. For those who have been in last year's ITAP, we actually brought this Ibuma burner down. It originally had 13 components combined to one. It had about 7 vendors and suppliers, which took us about 9 months to 12 months to actually fabricate. Today, we use design and our expertise and knowledge in AM with the help from our software guys who have developed the NXCAD to create a component, a single component combining all these 13 parts. What does this mean? I've removed 7 of my suppliers. I control my own quality. I produce these parts in-house within 10 weeks to 40 weeks, as opposed to the 9 months, 12 months. That is the power of additive in serial production in real industrial mode. And that's what I bring forth to you. This was the history of our journey. It started off, as I mentioned, with repair. We sliced off the damaged part. We put it in the powder bed 3D printer, and we sinter on and laser on the bed. And we have a refurbished part. That was the start of our journey. And we're using the original metal powder that was originally used for this part. And we kind of honed that design as we go along. We realized there's more that we could do. The Ibuma burner now is in serial production, as I mentioned. We're not printing prototypes. We're not printing one on each build plate. we're printing up to 6. 6 build plates in a very industrial environment. And this burner is the poster child for Siemens. Why do I say that? For anyone who has really done metal additive printing will know that post-processing accounts for 50% of the time and effort to spend on the part that you 3D printed in metal. This part, once it's built, is EDMY cut off the base plate, it goes straight into the machine. There's no post-processing required. We envision this will be the future, where it will be as easy as 2D printing. You print whatever you need, you cut it off, you put it in the engine. No need for post-processing. As much as materials is important, so is design, so is functionality. And because of all the expertise and experience that we collected in terms of data, we pushed it back to our software team doing NXCAD. And with all this data, it's all embedded within our software today, such that design today is so much easier. So some of the challenges that we face during this whole process. Powder material, yes, is key. Understanding the quality, where it comes from, is important. Knowing the right mix, knowing the right material quantity that you need to prevent corrosion, for example, is key. But that mix is not linear, as I will show you later on. There are other things that really affect the whole process. Interactions between the flowability of powder. What do I mean? During the powder bed exercise, we will lay 20 micron layers, 60 micron layers of powder for each layer to be printed. If the metal powder isn't concentric, isn't symmetrical, the flow, the spreadability will be difficult. That will cause one of the issues for defects in your final print. There is also interactions with the laser profile. Is it a pulse laser? Is it an intensive laser? What is the laser strategy of your machine that you're using? The grain sizes and interaction and hot cracking also makes a difference in terms of your final make. So material is just one of the components in this fairly complicated process that we had to go through a very steep learning curve over the last 6 years. And you end up doing final processing or post-processing, which I mentioned takes up the most time and the most money. How do we simplify this? How do we demystify this? We went on to collect all this data that we had. We needed to find a material that's easily weldable and yet has strength. We had complex metals that were strong but were so difficult to weld. So titanium, for example, is a very strong metal, but it was the easiest metal that we can additively manufacture parts. So even though the powder itself is expensive, the process is actually cheaper overall compared to other materials. We took in all this data, which is not publicly available. All this is all manual. All this data has been collected over hours and hours of research and development with my team in the UK and in Germany. And we produced parts. We stabilized the process, we stabilized the material with tweaks. Because each material is different for each different process. There's always an issue of hot cracking, whether in the solid state, liquid state, or strain H. So every time you print, you don't know what's going to come out until you actually get it. So we've done the feedback loop within our software to account for all these defects and damages. And we embedded it within our software so it makes it easier for the user going forward to design and taking in consideration all these after effects of printing. We took a very exotic material, Hastelloy X, which we use quite widely in our gas turbines today. It wasn't perfect. We had to do minor chemical tweaks to it to get the chemical stability right. It took us some time, but we have gotten there. So we have expertise in stabilizing these processes. There's still a lot of data that we still need to collect for other new materials that's being developed, but that's an ongoing process that we do day in, day out, because we're end users of the Siemens software. Inconel 939, similar. When you get it from your powder supply today, we had to tweak it to our application. So like I said, every application, you need to customize the powder for your application and for that build. It's not as simple as I'm going to take miraging steel and then plant it into my production for additive. Today, we have accumulated quite a lot of hours running operation hours on our gas turbine as a reference point because we use it in-house. We are also sharing this knowledge with our customers and partners and companies at large who are interested in this technology. We've acquired a company called Material Solutions in the last couple of years who does just that, doing additive manufacturing consulting and services printing beyond Siemens equipment and technology. Today, Material Solutions has been certified ISO, and most importantly, they are certified NetCat for welding. We are the 6th in the world that has this certification, the first in the UK. The rest of them are in the US and in Europe. How do we bring it into Singapore? How do we get this NetCat certification to support our aerospace guys? NetCat certification is a very stringent test that you require years and years of data collection and process enhancements in order to be able to print for aerospace. And that's a big market in Singapore today. If we can reach that certification, that level of standards, everything else should be easy to certify in that process. And today we have about 40 printers in the UK and in Sweden using the powder bed technology, which we feel that that's the technology for the high-end stresses we see in the gas turbines today. So my goal in the next couple of years with the launch of our Advanced Manufacturing Transformation Center is to accelerate the adoption of advanced manufacturing through simplification, through digitalization, and through collaboration. We're creating this ecosystem to bring in all our partners because we can't do it alone. We are at a stage where we need to bridge the gap between AM R&D to AM industrialization, and Siemens can't do it alone. And we are very significant partners in this event, in this journey that we're going on. From a Siemens perspective, why are we taking the lead on setting up the AMTC? We have, over the last 6 years, we've been acquiring companies in the software domain. And today, I'm happy to say that Siemens is actually recognized as one of the top 10 industrial software companies. We always hide in the background, we're always supporting our customers and partners. So you see all the some of the 3D printers out there, they have embedded Siemens technology and controls inside because we understand additive manufacturing quite well. We help them with the laser strategy, we help them to understand the mechanics behind what makes serial production in additive manufacturing possible. And because we know how difficult and how expensive and how time-consuming it is, we have enhanced our software design tools, the NXCAD suite, which includes the NX Design, NXCAD, as well as NX Chem. So we're developing the product, we design a product in NX, we have a simulation of a virtual product, of how it flows. We have automated cheat buttons, I would say, to optimize the lattice structure. We have a program called Heats that helps create options for you in terms of your design work. This is to simplify the adoption of design. You don't spend hours and hours on CAD trying to do your design. We have an option. And because we work with all these machine builders, we've also compensated for the lean and stresses and skews based on each of the different platforms that we have. After doing the virtual product, we go and look at virtual production in NX Chem. How does the machine actually does the build of the product? Is there any roadblocks? Are there any blockages of the movement of the arm? When you go to post-processing, is the CNC 6-axis, is it encountering any blockages? Is it manufacturable in the first place? We simulate that and then we put it side by side to a real case scenario where we have actual production going. That helps you shorten your decision cycle. That helps you reduce your commercial investment in deciding whether the product works. And finally, we actually deliver the final product to you. This was the very first start of our journey in additive manufacturing at our corporate technologies group in Germany. Getting inspiration from nature, we rebuilt a burner tip, which is cooled using fluid to endure intense heat at the end of the burner tip, you can see. So the initial start was just the fender design. We put in the base design in, we went to the heats. Heats optimized this design based on its requirements, based on whether you want it to be lightweight, low cost, fast to manufacture. Based on the material that we chose, this was the outcome. And you can see all the cooling curves is now in the green and blue zone, which means this is the perfect solution and design for this part. If you've done it conventionally through normal design work, you're never going to get here. We're going beyond conventional thinking and conventional design. We're using artificial intelligence and all the data that we've collected to optimize the design for the user, for the designer, and put it into good use. We want to simplify, as I mentioned, the steps to get you to a right design without spending the whole lots of money to go and actually build one and do destructive tests and flow tests on the desk. Not only do we do a product analysis of a virtual twin or digital twin of a product, we can also do the digital twin of the entire assembly. You put it into an entire system, whether it's a car with multiple AM parts. You see the flow, you see the dynamics, and you optimize the design. So it's not restrained to just the product itself. It's the whole entire assembly. One example is we had this bracket for Aerospace. We wanted to minimize the chunkiness of the look. We had automated lattice structures that we could choose that will optimize the structure based on your requirement on constraints. Yes, it may look ugly, but it serves its purpose. It is lighter in its weight. We envision on the A380 in the future, if we change the entire gas turbine blades with 3D printing with a lighter load, the airlines are expected to save about $70 million on fuel every year because of the lighter payload. This translates to immediate returns within the first year of flying. It translates to longer distances they can fly. It translates to more payload they can carry beyond just the fuel that they need to harness. We'll make it simplified and easier for the user to get to where he needs to go based on our years of experience and knowledge. Another example of the lattice structure, we create options for the user based on the kind of design he wants, based on the constraints that he has put into the system, all at the touch of a button. We created conformal structures, both from the skeleton and for bones, to improve the design. We know all the benefits of AM. It's how do we bridge this gap and how do we get there to zero production. Today, we have a lot of examples and that we're trying to help encourage the industry to move forward. This is our Experience Center, AM Additive Manufacturing Experience Center in Erlangen in Germany, showcasing all our partners of 3D equipment with our knowledge embedded into it. It showcases HP, EOS, DMG, Moey. If you had a chance to visit, please do. It will give you a whole experience of what AM is, from the design phase all the way down to production and to post-processing. Beyond just creating the product, the assembly, and the simulation, the digital twin, we also have created a product called Technomatics. Technomatics is what we call a plant simulation. We can virtually develop the entire AM production line for you in a virtual mode. Understanding how to optimize, how many machines do you need, how many post-processing equipment you need, what size do you need today for the maximum utilization, and how much more do you need to grow in the future when you want to expand. Plant Sim or Technomatics helps you do that layout. All this can be done in the Siemens suite, where you can see from production or the design phase all the way down to a factory layout. Saving costs, saving time, and avoiding mistakes. One unique part about the AMAC, I must say, is we have partners in there which continuously develop their capability with us. We talk about materials. Every time we develop a new material alongside our partners, we help them to develop the laser parameters and strategy for developing the right parameters for that material that is developed. So we're in tandem, we understand how it works, and we want to help our partners succeed. Material Solutions was a company I mentioned earlier on. Is a company we acquired in the UK. Its pedigree is aerospace. It's been working with some of the top aerospace equipment builders in the UK. We have been qualified as one of their key suppliers, and most importantly, we're NetCap certified for AM welding specifically. Today is about 50 EOS printers. They are in serial production. We're not talking about prototyping anymore. How does Singapore get to this stage? How do we accelerate the adoption of additive manufacturing to the industrial stage in Singapore? With an end-to-end solution from Siemens, along with our partners in this ecosystem, we want to bring this to you. We have set up the AMTC, Advanced Manufacturing Transformation Center. How can you be part of this ecosystem? How can we bring you to the next level? How do we bridge the chasm between AM R&D and AM industrialization? We want to simplify, we want to digitalize, we want to teach you how to do it yourselves. The aim of the Transformation Center is to bridge the understanding between I want to produce prototypes in R&D to how do I train my operators on the production floor. With the ecosystem of our key partners, powder, materials, metrology ties, certification bodies, and most importantly, the printers and the post-processing CNC equipment. All this housed within an ecosystem that is there to support you through your journey to additive manufacturing industrialization. Do join us at our booth, where my colleagues will show you the raft of the digital twin products, the technomatics, where we show you the plant simulation of one of my additive manufacturing factories, how we automate this, and how powerful it is to help you save money and make a better decision. We are just outside, just down the line. Please look for me. My name is Benjamin. Please come and see us for AMTC. Thank you.